Over 13 million Americans, or roughly 13% of the population 12 years or older, suffer from disabling hearing loss in both ears. Lectio Signum intends to be a real-time, mobile American Sign Language, or ASL translator that will help bridge the gap between ASL users and English speakers. Lectio Signum consists of two bands that will be worn in unison in order to collect biological signals consisting of muscle activity and arm movement. This data is then processed and classified, resulting in a displayable translation through our user interface. Ultimately, we intend for Lectio Signum to remain affordable due to social inclusion purposes. In order to remain comfortable, we intend for the device to be light and ergonomic and to be able to fit a vast array of arm sizes. Lastly, in terms of our real-time goal, we intend for the device to have 80% accuracy in translation with a maximum delay time of 2 seconds.
The device consists of two separate bands. The arm band includes electromyography or EMG sensors, which detect the electrical activity due to muscle contraction. The sensors are housed in 3D cases custom designed by the team and are attached to the forearm muscles. The raw signals are then processed using active bandpass filters. The filter signals go through a microcontroller board called the Arduino Nano to the computer. The other band includes an inertial measurement unit, or IMU, that records the acceleration and angular velocity of arm movements in 3-dimensional axis.
The Lectio Signum desktop application serves as the main user interface. The application will handle receiving, cropping, and classifying ASL signals and translating them into English, text, and audio. The machine learning model implemented is a random forest classifier that takes statistical parameters such as standard deviation and root mean square as inputs and outputs the gesture performed.
To make sure the system works, we first built 4 bandpass filters and tested their response using body plot analyzers. Then, we connected electronic components and tested them by acquiring signals. Lastly, we assembled the component into the 2 bands. For the EMG band, we soldered the sensors and the filters and connected them to the Arduino and batteries. For the IMU band, we connected the accelerometer to the Arduino board and powered them with a battery.
To test the accuracy of our signal processing and classification algorithm, we collected data from 2 subjects using the Delsis-Trigno EMG system. We collected 13 distinct generic hand gestures, 20 times each, and obtained a 92% accuracy when classifying them. We also recorded a smaller data set using the Lectio Signum EMG band. We recorded the gestures of L, no, S, and yes, and using a data set of 46 samples, we obtained an accuracy of roughly 90%, which is yet to be iterated with a larger data set.
Based on the total cost, the production capacity for the project can reach up to 92 devices in the first year, with a sale price of $800 per unit.
After 1 year of working in Lectio Signum, we have accomplished many of our objectives. We have successfully developed the hardware and software necessary to collect EMG and motion data from the user of our bands. Using preliminary data, we have constructed a machine learning classification algorithm that can successfully predict hand gestures based on biological signals. To continue our work, we plan to extend the gesture dictionary, implement Bluetooth connectivity, add two-handed compatibility, and transition our UI to a web application for more versatility.